Enols. Enols.
No, let's not do it like that. This chapter is called Enols, Enolates, and alpha carbon. Okay, you guys know about enols, yes? Who does not know? Pitbull, do you know about enols? You don't?
No idea, professional.
It's too bad for you.
Terminal alcohols.
Enols and enolates, yes, is from tautomerization. Okay? This carbon here is the carbon we're looking at. The carbon next to it, or the carbon next to the carbonyl, is called the alpha carbon. And after letter alpha comes letter
Beta.
beta. Outstanding.
And then gamma.
And after beta comes
Gamma.
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 It's a
Is this
Y.
gamma?
Yeah.
Is it?
It looks like a 2.
It looks like alpha.
It looks like ear tubes actually.
I don't know, is that gamma?
I don't know.
Is this another alpha?
Yeah.
Yes.
This another beta?
Yeah.
And this is another gamma. Okay? Alpha protons are acidic. The alpha protons to aldehydes and ketones are acidic. Now, how acidic are they?
Very.
No, they're not very acidic. They're not very acidic. But I have a question for you. Because I have explained to you stuff.
Of what's more acidic? The bottom.
What's more acidic? Proton here or proton here? The alpha protons.
The top. The top.
On the other hand.
Which one is more acidic?
The top.
I say
Top?
The aldehyde.
I say the bottom.
Top or bottom?
The top. T-O-P.
Side.
Reacted.
Wait,
My
aldehyde.
question is, why is it more
Because of
acidic?
the hydrogen. Yeah. Yeah.
Because steers relax.
It's because this group here, and I have already mentioned this before,
Aldehyde is
because this group here is electron what? Is electron pushing, electron donating. So this is going to actually
Even
send
out,
electron
yeah.
density this way. And what you want is to take it out. Of course, this is the norm, yes? This is
Right.
not doing anything. Versus this is pushing it.
Right.
So which one is more acidic? That one is more acidic.
Well, aldehydes are more reactive than ketones anyway.
Well, but they're more reactive, but that has nothing to do with being more acidic. Because they're more reactive doesn't mean that they're more acidic. So, we have this. And keto-enol tautomerization goes like this, yes? What is the enol of that ketone? Why not, man? What do you mean you don't know enols? Didn't you have that in 1045?
I had a rough time.
When you said that the hydrogens on the alpha carbon are acidic, is that the same reason why it gets attacked in the NM formation?
In the what?
When we're making NM,
Enamine.
is that,
Yes, that's precisely
is
the
that the
reason.
same hydrogens that you're referring to?
Yes. That's why they get attacked and they get pulled off easily.
One had 2 hydrogens.
Yeah.
So what we are going to have here is, there is a hydrogen from here, yes? Yes or no? This hydrogen is going to get pulled off. And then at the end, if we're looking at one molecule, yes? This hydrogen will go here, this double bond will go there. This is called keto, and this is the enol. And this is called tautomerization. Which one is more stable? Where does the equilibrium, this equilibrium, yes or no?
Yeah.
Equilibrium.
Mhm.
So do we have both of them at the same time?
Yeah.
Yes. We have both at the same time. Which one is more stable?
Keto.
Keto
Keto.
Because you have enol that is gonna turn keto.
You all chanted Eno.
Oh,
I
you're
see.
right, because it says to react the ketone, you have to convert it to the enol form. So the keto is more stable.
No, you're supposed to know that the keto is more stable because I told you an organic one.
Yeah.
That's how you know.
See, that exam was really.
I told you,
That's the stuff
and I was told too. So if it is or not, I don't know. Okay, but this is more stable, yes? So where does the reaction lie? The equilibrium is to the left. So there is a ratio of these things, yes? A ratio. In this case, maybe there is 1% of this and 99% of that, or 5% of this and 95% of that sort of thing, okay? So when we are doing this enol reactions, we are going to use this carbon-carbon double bond as the electrophile or nucleophile.
Has electrons.
Double bond can be a nucleophile or electrophile. I remember, I did it over there last week. Because it has electron pairs, yes?
Yeah.
So this is going to undergo an attack like that. It's going to attack stuff. Like, can that be an attack?
Yeah.
What do you think?
Yes.
Yes, of course. Because here is a nucleophile,
Yeah.
and here is an electrophile alkyl halide. How many times have you seen this such thing? 1,000 times. This is not different. If you learned this from before, this chapter should be cake for you. If you did not learn it from before, like Pitbull over here. So, this is a resonance structure of this. This is a resonance structure of this. Let's say that this will make a double bond there. This will be positive here. Yes, and this carbon here is going to have. You agree, yes or no? Hello? This double bond goes here, those electron pairs goes up there. So this is the negative. And this is also going to do the attack on the electrophile, okay, or electrophile. So in the class, we can either draw a mechanism like this, or we can draw one like this,
Okay.
okay? Now, of course, this, even if it seems a little weird, okay? We're not showing you the correct way. All I'm showing you here is, because this will more than likely look like this, yes? Okay? How it's going to look is like this. But I didn't, all I showed you here is attack from the double bond or attack from
The lone pairs?
The lone pair.
this here, okay? Of course, this happens because of this. The bases that we can use, the pKa, is around 16, okay? Let's say I use this base, an alkoxide. This is called alkoxide, yes? Is that called alkoxide? Like sodium. Okay? This is a base, and what this is going to do under, it can happen under acidic conditions or under basic conditions. These conditions are
Basic.
conditions. This proton is going to get pulled off,
Yeah.
and these electrons are going to go where?
To the carbon.
These electrons are going to go to that carbon. I could draw a resonance structure in which these two electrons
Go
go
to the
here.
double bond. Yeah.
and I go there, yes? I did not do that because I want to show you where the electrons are at. Okay, so if I pull that, this is what happens. You agree, yes or no?
Yes.
That's under basic conditions.
Mm-hmm.
And a resonance structure to this is,
Yeah,
Electron
double
go
bond,
here.
and then that goes up.
and that goes up. And what you have is,
O negative.
yes or no?
Yeah.
Now, what I'm telling you is that in this class, most of the time, the one that I am going to show making attacks is this one. Okay? I am not going to make the attacks from the resonance structure, from this resonance structure. By the way, which one is a better resonance structure?
The second one?
Second one.
The second one. This is a better resonance structure, yes?
Yeah.
But it's difficult to show you attack from here.
Mhm.
So I am going to show you the attack from there.
Okay.
Okay? Now let's say, let me give you some numbers. The pKa of this is 16.7. And the pKa of this is 15.9. No, you don't have to remember it. You do have to have an idea
Yeah.
of what is everyone knows from before that the pKa of an alcohol is more or less where?
16.
16. The pKa of water is
Lower,
a little bit
lot
lower than that, yes?
Mhm.
The pKa of an amine is,
Higher.
17.
yeah, higher, but where higher? Like in the 30s. But it changes depending on the structure. But the pKa of ammonia is around 36, yes? The pKa of an alkyne is where?
High.
Alright.
High.
Where, more or less?
Like
You have to know the rules. No, it's not a 50. An alkyne.
Oh. More acidic.
It's more acidic, yes. So an alkyne is more acidic than an alkene, which is more acidic than an alkane.
Alkane. Right.
So you're talking about pKa's for alkynes in the 20s, right?
Mm-hmm.
23, 21, 23, 24, 25. pKa's of an alkene, which is 40s, yes?
Yeah.
And pKa's of
Alkane.
sp3 hybridized 60, 50s,
Okay.
okay? Guys, yes or no?
Yes.
pKa's of carboxylic acids around where?
4.
Five.
4. Right.
4, 5,
Five,
3,
yeah.
okay. After carboxylic acids, what comes next? After carboxylic acids, you can have water and alcohols.
Mm-hmm.
Depending on the alcohol, you have even phenol has a pKa of around 9, yes? So phenol is very acidic because
The residence.
because of resonance stabilization. After that, you have water, and then you have alcohols, and then you have triple bonds, and then you have amines, and then you have alkenes, and then you have alkanes. Yes? So you expect this, they're all sp3 hybridized, yes or no?
Yes.
These. So the pKa of this is abnormally low. Why is this so low?
Because it's sp3.
Why is that pKa low? Why is that proton acidic? Because of resonance stabilization, yes? It is stabilized by putting the negative charge here. Okay? So which one is more acidic? That one is more acidic. So if I have this, and I bet you're not going to remember. let's say I have this. It's 1046, yes? Does this reaction go forward or reverse? Where does the reaction go mainly?
It goes the opposite way when it's acidic.
So the one over the lowest.
Don't explain it to me. Tell me, forward or reverse?
Reverse. That has the most acidic right there. So
Which
those
one is
are
the more
opposite.
acidic?
The right side, the alcohol.
This is more acidic, yes?
Yeah.
So the
So it's
reaction
gonna go
goes
opposite.
reverse. Now, this is what type of reaction? This is an equilibrium.
Equilibrium.
What that means is, when you add this to that, some of the protons get pulled off. How many is a different story. Some of them get pulled off, and you form this. The reaction mainly lies to that side. So if you start having more and more of these, what happened? They react with this and give you that, okay? So their reaction does not go to completion. This is reversible. Yes, it goes back and forth. If you add sodium hydroxide, so I'm going to say this reaction is reversible
Reversible.
because it goes back and forth. So this formation of this enolate, you will form this enolate, and if it reacts, you are decreasing this concentration, yes? And if you decrease this concentration according to the Chatter's principle, what happens?
It's
Then you
gonna go
form more
forward.
and
Yeah.
more and more. So the reaction can be driven to completion if the product, okay, does not go back. Okay, if the product goes back, then it will go back well, however many steps. Now, you have something like this. And let's say, let's just call it H minus. And the pKa of H minus is higher than 16.
Mhm.
But that is not the purpose. The purpose is not how basic it is. The purpose here is this reaction will do this again. Now tell me, what happened here? Is it the same reaction as above?
Yeah.
Still a base, yes?
Yeah.
Yes.
And by the way, is this a nucleophile too?
Yes.
Is that a nucleophile?
Yes.
But here we're using it as a
Base.
Base.
In other cases, it's not a base. So,
It takes
you
a
made
proton
this
from
here.
there.
It's the same, yes? But is this a back and forth?
No.
Is this an
No.
equilibrium?
No.
No. The answer is no. And the reason for that is here. Because this is H2 gas. And the H2 gas does what? Bubbles out of the solution. So even if it was reversible, you continue taking that out, the reaction continues to go forward. But this is, I am going to say, this is a way of irreversible. Okay? There is more ways of doing this irreversible, and one of them is using a stronger base. And that stronger base is called LDA. You ever heard of LDA before? What do you think the L stands for?
Lithium.
Lithium. And the D?
Die.
Di. And the A?
All the time.
Amide.
Amide.
That's why before, when they used to write this for you, and I saw, I don't like dipole. Okay? What do I call this in this class?
Diball.
I call it diball, yes? Because it is two
Balls.
outstanding. How can you forget, right? Come on, man, we already talked about this.
Better than one.
Alright, so this means, okay, not this one. LDA means
Lithium.
diisopropylamide. Okay, so here is the nitrogen.
Mm-hmm. Oh, okay.
It's called diisopropylamine. yes?
Diisopropylamine.
If I take one of these hydrogens away, let's say with this lithium, you will get negative charge, yes?
Yes.
What is the pKa of this? pKa of this is in the 30s, yes? In the 30s. In the 30s, maybe even 40, I don't know. So, when you treat this with LDA, okay, because it is so basic, it generally does not go in the reverse direction. So that is also irreversible. So this is diisopropylamine. This is called lithium. Diisopropyl amide. And this amide is called amide because it is negatively charged. It is not an amide from a carbon, oxygen, double bond, and a nitrogen, okay? Sorry. I hear some of you guys picking up. Why are you picking up? Okay? Yes or no? Let's say I add a base. What is it going to do?
Extract the proton.
Abstract the proton to form, what is it called?
A double bond, right?
Is it an enol?
It's a,
Maybe called an enolate, okay? It's a negatively charged enol, yes? It's gonna form a carbocation here, a carbanion here. Okay, yes or no?
Yes.
And if I add Br2, what do you think that is going to give us? Okay? This hydrogen gets pulled off by the base, and this carboanion here will then attack this bromine, yes? And that bond will break, and it will form Br minus. So this is called the alpha bromination.
Alpha bromination.
How do you like that?
Nice.
What time is it?
Number 25.
Some of you guys are anxious.
Got 5 minutes.
What are we going to continue doing in this chapter? We are going to continue doing that with a base. What else can we add here to this side? Can we add like an alkyl halide? We add a base and an alkyl halide, and what do we get? Alkylation, yes. We get a longer chain, yes?
Yeah.
Longer chain. Can we add a carbonyl? Hello?
That carbon.
Guys, nucleophile, can we add a carbonyl?
Yes.
Yes, we can add a carbonyl. I mean, I don't know how many times. I mean, if you add a Grignard to this, what do you get? No, Mg, okay, fine, but if you add a Grignard to this, you're not making a Grignard, you're adding. You get an attack here, what do you make? An alcohol. If we have this negatively charged here and we make an attack there, what do we get?
An alcohol.
Okay, and how is it gonna look? This is gonna look weird now. Let's say I have that one, that it attacked. This is what I have, yes? That's what I have. And it attacked that and it made an alcohol,
Alcohol.
maybe after you add a proton source. The carbonyl will still be there. Now you have the carbon where you took it off, and now you will have a bond to the carbon that had the carbonyl. This one had an oxygen. It will be negatively charged. That's that oxygen. What else did it have?
Another
CH3 and a CH3. If you add a proton source to this,
Then it's going to be alcohol.
what you are going to have is
Tertiary alcohol.
that is what you are going to have.
Tertiary alcohol.
Yes or no?
Yep.
Do nucleophile attack esters and amides or not? Hello?
Yes.
That's called the aldol.
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 But it's okay, don't worry.
Like the
I'm
shape
just
outline?
I'm just lubricating you right now, so you don't need to know. Okay, the first one was called alpha bromination. Don't worry, we will do more next week. I mean on Thursday.
Alpha bromination.
You know what? Let's have a quiz on Thursday.